Hi everybody, welcome to Excel Video Notes 1.1. Your friendly neighborhood chemistry teacher, Mrs. Harbin. I have a song playing in the background that I'll make sure to get you the link to so that you can use it to help study. So today's PowerPoint is going to go through these two main points. These are two objectives that I hope you get after listening to this. Okay. I referred you to some pages in the book to read already, but I specifically referred to them again, and I'll remind you when we're there. So it's good to have your book with you when you're listening to these video notes. Just because this is a chemistry class and we haven't even talked about it yet, I want you to know what chemistry is. It's the study of matter and the changes that take place in matter. All kinds of changes, chemical changes, physical changes, changes in heat. That's all the kinds of things we'll be looking at this year. Okay, but we need to know what matter is, and one of the first building blocks of matter is understanding the atom. Way back in ancient Greek times, there was a man named Democritus, and he's often given credit for being the first to talk about an atom, being these tiny pieces of matter that were indivisible or couldn't be broken into smaller pieces. He didn't actually have any evidence for this, so his theory was actually ignored for several years because of people like Aristotle who didn't think atoms existed. So for instance, who could do this? Maybe Chuck Norris, but we have no evidence that Chuck Norris was there. So Democritus's ideas were kind of set aside. Please look at page 78 of your book for more information on this particular slide. But John Dalton was the first scientist to take all kinds of chemical data, evidence from other people's experiments, and come up with a theory. And based on evidence, he was able to come up with these four main ideas. And some of them are currently still true. Some of them had to be modified a little when we find out new information. So here we go, that all matter are made up of these particles called atoms. He thought they were indestructible. Atoms of the same element were identical. Compounds are formed by combining two or more different types of atoms. The reason there's an asterisk there is because just combining doesn't work. Chemically combining does. And then chemical reactions are rearrangements of atoms. So we had evidence to back up these four main postulates. So some of the evidence was something like this. So if you took a compound that if you took some mercury and sulfur and reacted them, you got a new compound called mercury sulfide. And it was different, but every time you did it, to get that compound, you had these percents of each element in that compound. And so there's some evidence, scientific evidence or data to support the theories. Okay, so again, here's some of Dalton's postulates, main ideas. These ones are still true. All matter is composed of atoms. Compounds form when two or more atoms combine and chemically combine, and the relative number and kinds of atoms are constant in a compound. So that means that H2O is water's chemical formula, and it's never H2O4, HO for water. It's always H2O. Relative number and kinds of atoms are constant. These three ideas were true for his time because it's all the evidence they had. But these all had to be modified based on what we know now. Okay, so let me just take you back here. Same mass. Well, we know about things called isotopes now. Different elements have different masses. We know there's some elements that might have atoms that weigh the same as others. And indestructible and indivisible, we know about parts now of an atom. Okay, we know atoms can be split in fusion or merged in fission, merged in fusion. We'll talk about later in the chapter. Some atoms of two elements may have kind of the same mass, and atoms have isotopes. So those are 3 points of Dalton's ideas that had to be modified based on evidence. So if we took Dalton's ideas and made a model of the atom, it would be called the billiard ball model. What was good about it? Because we were finally talking about atoms existing. What was bad about Dalton's model is that he had no knowledge of protons, neutrons, and electrons, didn't know where they were, and you can see that his postulates had to be modified when we got new data. Okay, so model of the atom is the billiard ball for Dalton because he just thought atoms were indivisible spheres. Okay, more evidence. Look at page 81. There's a description of this piece of apparatus. This is so please make sure you know what this is called. This should help, and make sure you know what this experimental piece of material is called. But J.J. Thomson used it to discover the electron, and then he discovered that the electron was negative based on that. Okay, so let me just say that this was a beam of cathode rays they called them. Okay, and the cathode rays deflected. This is a positive charged plate, and this is a negatively charged plate. Okay, so the cathode ray was the beam of electrons. He discovered that this beam had a negative charge, and he discovered that all atoms produced this beam. Every atom he tested produced this beam. It was lighter than any individual atom, so it had to be in the atom and had to be part of the atom. Called it the electron after he determined the charge. So what kind of model of an atom can be developed with a well, it's called a plum pudding model. So this is kind of like the positive dough all around. So you have this positive dough all around, and within that were embedded these tiny, very light mass, meaning it had not much mass, with a negative charge. So what's good about this model? It's an atom, yay. It's also good now it has electrons in it. What's bad? Well, we know about a nucleus. This had no nucleus because there's no evidence of a nucleus. No protons, called that the positive dough, and no neutral charges, so no neutrons. So we are further developing. We went from billiard ball to plum pudding. Okay, Ernest Rutherford, please look at page 82 of your book and be able to describe this gold-foiled experiment. Okay, what this gold-foiled experiment did was help Rutherford discover the nucleus. So based on the evidence from this experiment, which we'll discuss in class, he discovered that there is a small, positive, and very tightly packed together or dense part of an atom. He called it the nucleus. Okay, and the electrons that were discovered by Thomson were still there, but they were outside of that nucleus. All right, so the nucleus is a small, positive, and dense material inside an atom. Electrons are outside the nucleus, but also in the atom. And this experiment, the gold foil experiment, helped to determine that. What's bad about this is we still don't know how those electrons are arranged outside. Okay, Niels Bohr, please look at page 311 in your book. Okay, he was able to do some experimentation with spectral lines. Spectral lines were the experimental evidence that he used to predict the energy of the electrons within an atom. Okay, so he was able to tell based on the specific lines that were the fingerprint for different elements. He was able to determine that electrons were in energy levels, which is good. So you still have the nucleus. Okay, you still have that nucleus is positive, and you still have the electrons, but now the electrons were said to be in energy levels. He described them as rings or orbits, but that's wrong. Look, that's spelled wrong, because wrong is spelled like this. Rings are wrong, but what's right about the planetary model was that the electrons were in energy levels. Okay, so we still have a nucleus, we still have protons, neutrons, and electrons, and we know that the electrons are in energy levels. What's bad is the rings. So we no longer use this planetary model to describe the atom. Today we use the quantum mechanical model. Quantum, whoops, I should spell it right? Quantum mechanical model is what our current model of the atom is. Quantum mechanical model, QMM. That's today's model. So up until right now, we're still using this model. Two scientists involved were Schrodinger and Heisenberg. It's a mathematical description of where the electrons are. Still agree, positive nucleus with protons and neutrons. Electrons in energy levels, but those energy levels aren't orbits, they're probability clouds. Okay, and so kind of like these clouds, and we can't tell exactly where an electron is. The Heisenberg uncertainty principle, you can't tell exactly where an electron is and how fast it's moving at the same time, because if you know one piece of information, you can't know the other. But they're probability clouds. Those clouds are called orbitals. Probability clouds called orbitals, but not orbits. Okay, so here's a mathematical description of what an atom looks like. Nucleus in the center, different clouds that describe where the electron could possibly be found. please look at page 313 and 314 as you're doing this or after you do this to see what I'm talking about. Okay, those are called orbitals, those probability clouds, and those orbital shapes are described mathematically by the Schrodinger equation. Schrodinger, yeah, that's that guy. His equation helps describe the shapes of these clouds. Okay, so to review, please know that there are protons in an atom. That's one part of an atom. Protons are in the nucleus, small, dense center of the atom, positively charged. Protons are positive. 1 AMU is the relative mass of a proton. That means compared to other parts and other things, it has a mass of 1. A neutron also has a mass of 1. Okay, they weigh about the same in actual grams, but instead of saying their actual mass, we call it 1 atomic mass unit. Okay, what is a proton for? It helps determine the identity. Hydrogen has 1 proton. Lithium has 3 protons, or else it's not hydrogen or it's not lithium. Okay, that's a P plus for proton. If it doesn't have the same number of protons, it's not lithium anymore. Okay, neutrons are also in the nucleus. They're neutral, no charge. They help determine the mass and stability of an atom. Electrons are in clouds, electron clouds outside of the nucleus. Negative charge, negligible, I can't even say it. Negligible mass means they don't have very much mass. In fact, it's about 1/2000th of an AMU. Okay, so that means it's 2,000 times lighter in mass than a proton and a neutron. Okay, so it's very, very small in mass. It actually has an actual mass, but it's negligible compared to 1 AMU of a proton and neutron. Electrons help determine the charge of the atom. If there's equal number of protons and electrons, the atom is neutral. If you lose or gain electrons as an atom, you become charged. Okay. So to review, models explain and display what scientists know, and models progress as new knowledge comes along. But it's based on experimental evidence. Make sure you know the experiments and what they showed about our theory of the atom and the development of atomic theory. Know what protons tells you, know that rings are wrong. And to take you out, I'll play the song again. Please look at the pages I referred to, and I reminded you of those pages. Put that all in your notes. An open note quiz coming. Please be ready. Hopefully, if you read these real quick, you can determine those things. Okay? Thanks. Peace out.